In this set of videos, we're going to look at rigid body impulse and momentum methods. As we saw with work and energy methods, these offer an alternative means to solve rigid body kinetics problems. You may have seen in your study of particle dynamics the concept of impulse and momentum methods. To remind you, there is such a thing called the principle of impulse and momentum, which states that the system momentum at time 1 plus all of the external impulses between time 1 and time 2 is equal to the final system momentum. Now, if some of these concepts are perhaps a bit far back in your mind, don't worry about it. We're going to look over all of these terms very shortly. As I did with work and energy methods, I want to ask the following question. Where does this idea come from? That is, where does the principle of impulse and momentum come from? Is it a new fundamental law of nature, or is it perhaps derived from another one that we know quite well? So, as we did with work and energy methods, we're going to start with Newton's second law, which states that the net force is equal to the mass times the acceleration. This can also be expressed as the time rate of change of mv, right? Because we know that the time rate of change of the velocity vector is equal to the acceleration vector. And for a rigid body, we can take the mass out of the derivative, so we just end up with something of the form m dv by dt, which takes us back to our original form of Newton's second law. But let's focus on this formulation over here. You may recall from high school that the term in brackets can be expressed as the quantity p, and this is called the momentum vector. And since we're dealing with rigid bodies, I'm going to call this the linear momentum vector. That is, p is equal to mv. So this should not be a particularly new concept. We know that the momentum is equal to the product of the mass times the velocity. But now what we're going to do is that we're going to rearrange this. Okay, so we're going to rearrange it so that we have the force multiplied by the differential time dt is equal to dp, the change in momentum. And what we're going to do, we're going to integrate between time 1 and time 2. And so what this is going to give us is p1 plus the integral from t1 to t2 of f dt is equal to p2. So this one up here would be integrated between p1 and p2. Okay. So this is our principle of impulse and momentum. So this is momentum at time 1, and this product over here, a force multiplied by a time, or a force applied over a period of time, is what we call the impulse. And this is the momentum at the final time. So we can think of many examples of an impulse, right? So let's say the thrust from a rocket applied over a certain period of time, let's say stage 1 of the launch of the rocket, that could be a certain impulse, okay? So This is our principle of impulse and momentum as we know it. So now, as we have seen in our study of rigid bodies, oftentimes it's not as straightforward as particle dynamics. That is, that we might have additional terms that pop up. So the question is, here we have a linear momentum P. And we have an impulse that is the product of a force and time. So now, when we're concerned with a rigid body, the question is, are there additional terms? That is, are there additional forms of momentum? And are there additional forms of impulse that are possible for a rigid body? So we're going to seek to answer this question in this video. So to answer the question of whether there are some additional terms in our principle of impulse and momentum for a rigid body, what we're going to do is we're going to look at the moment of the linear momentum. So here what we have a random bean-shaped object in yellow. It has a center of mass located at G, and we have a local coordinate system x prime, y prime. And we're going to look at a particle that is within this rigid body. We'll call this particle I. And so what I drew here, the vector in red, is the particle's momentum vector, which we call Pi. So let me just write this out here again. So Pi is equal to Vi delta Mi. And so note here that Vi is the relative velocity with respect to G. Okay? So it's not the absolute velocity, it's the relative velocity. And as I'm going forward, I'm just going to drop the prime notation here, but just recall that this is relative to G. Okay? So every particle that comprises the rigid body has its own individual linear momentum, depending on the local velocity vector, Vi. Now, the angular momentum of a particle is obtained by taking the moment of the linear momentum of the particle. And now, we can take moments about any point that we like. So here, it makes sense to take the moment about G. So let's write this out. So we have the moment of Pi with respect to G, or should we say about G. Okay, and so this would take the form of our moment arm, Ri, and we're going to cross it with our linear momentum, Vi delta Mi. And what we call this the angular momentum. So this is the angular momentum of particle I about the axis passing through the center of mass, G. Okay. So it's not very useful to have the angular momentum of an individual particle. What we care about is the rigid body as a whole. So we can take the summation of all the individual angular momenta to give us the angular momentum about the center of mass G for the entire rigid body. And so this would be of the form Hg is equal to the summation over all the particles that comprise the rigid body of the moment of the linear momentum vector of each particle. Okay, so we're just performing a summation over all n particles that make up the rigid body. So notice that for a rigid body, it might be undergoing general planar motion, it might have an angular velocity omega, so we can express Vi in terms of its relative velocity, right? Vi is a relative velocity relative to g. Okay, so let's express this as the summation from I going from 1 to n of our moment r crossed with, now Vi, again, the relative velocity. So recall this would be of the form Vi with respect to g would be omega crossed with r I. And then we multiply it by the mass of our particle. Now this can be simplified, right? So notice that for a rigid body, omega is going to be constant throughout, right? We cannot have a different angular velocity at different locations on the rigid body. Otherwise, we would not be dealing with a rigid body. So that can be taken out of the summation. So if we take this out of the summation, we would note that the magnitude of hg would be of the form omega multiplied by the summation of Ri squared delta m I. And as we shrink these particles down to a differential size, then what we would have is something of the form r squared dm. And hopefully this integral should look familiar. This is our mass moment of inertia. And we've looked at this extensively. So the mass moment of inertia is a measure of the distribution of the mass throughout the rigid body relative to a certain point, and in this case, this point is g. So we call this Ig, the mass moment of inertia about the center of mass g. So what this gives us, this tells us that the angular momentum of a rigid body is equal to the mass moment of inertia multiplied by the angular velocity omega. So hopefully you see that there is a certain analogy to the linear momentum. So the linear momentum is equal to the mass times the velocity. And I've tried to point these out in previous videos where we see that there is an analogy between our rotational equations of motion and our linear equations of motion. So in the linear momentum, we have the linear momentum is equal to the mass times the velocity vector. So let's look at the right-hand side of the angular momentum. So we have a velocity vector, but in this case, it's an angular velocity vector versus a linear velocity vector. And now our constant of proportionality, if we will, instead of being the mass, it's the distribution of the mass. Okay? So both the angular momentum and the linear momentum take very similar forms. And because we're dealing with a rigid body, what we need to do is come up with a convention of, well, where we're going to evaluate the linear velocity for the linear momentum. And what we need to do is say that we're going to evaluate the velocity at the center of mass, g. So now, given that we've found that we have an additional form of momentum, which is the angular momentum, we have our principle of impulse and momentum for a rigid body. And so in the xy plane, we will have the initial momentum in the x direction plus all of the external impulses between time 1 and time 2 in the x direction will be equal to our final linear momentum vector in the x direction. We can do the same thing in the y direction. And finally, we will have our rotational or angular momentum. So we will have the initial angular momentum plus the impulses. So now what do the impulses look like? So instead of a force multiplied by time, we will have a moment about the center of mass, or all of the net moments about g. Okay. So here we have three scalar equations. Two linear impulses and momentums, and one angular impulse and momentum. So this is our principle of impulse and momentum for a rigid body undergoing planar 2D motion. So as we did in kinetics, we can develop kinetic diagrams. Okay, so let's say we have a rigid body. I'm going to try to duplicate it here if I can. And so what do we have? Okay, so we might have every single particle has its own linear momentum vector. So if I call this pi over here. And this is equivalent to just drawing this as having a linear momentum vector at the center of mass and an angular momentum vector about the center of mass. So the question arises, what if we want to have the momentum be computed about a point other than g? So what we do, so if we want the momentum about point O, how would we go about it? What we'll do is that we'll take the kinetic moments about point O. So the kinetic moments. And this is as we did with rigid body kinetics. So we look at our kinetic diagram over here, and we see what exerts a moment. So perhaps it'll be better if I draw this over here. So let's say we have a point O over here, and this distance here would be, we'll call this RG. So if we take the kinetic moments, what do we have? We have IG omega plus the moment due to the linear momentum. So we're going to have mvg multiplied by rg, the moment arm. Now, given that this can be expressed as omega rg, we can factor this out. So we will have mrg squared multiplied by omega. And this is our parallel axis theorem, which gives us the mass moment of inertia about point O. So what this tells us is that the angular momentum about point O is equal to the mass moment of inertia about point O multiplied by the angular velocity. Okay, so let's recap what we did. We reintroduced the concept of the principle of impulse and momentum. We performed a quick derivation to show that this is not a new fundamental law of motion, but rather it is an integrated form of Newton's second law. This led us to the question of when we're considering a rigid body, do additional terms appear? That is, are there different forms for the momentum, and are there different forms for the impulse? So in a linear sense, we have a linear momentum plus a linear impulse, which is a force applied over a time. And so is there such a thing as an angular momentum and an angular impulse? And in fact, there is. By looking at the moment of the linear momentum of each individual particle and then taking its summation throughout the rigid body, we find that the angular momentum about the center of mass, g, is equal to ig omega, which leads us to the principle of impulse and momentum for 2D rigid body motion, where we have three scalar equations, two for the linear components, x and y, and one for the angular component. In the next video, we're going to see the application of the principle of impulse and momentum for a rigid body.